Point B is 300 kilometers east of point A. A plane which can do 100 kilometers per hour in still air flies from point A to B and back to A. A wind is blowing from the east with speed 10 kilometers per hour. So initially the plane is at point A, so the letter P stands for the plane. The velocity of the wind is minus 10I because the wind is blowing from the east, so it's a vector pointing to the left. It has no j component. Its magnitude is 10. It is pointing in the minus I direction, so VW is minus 10I. Now we can think of vector VW as the velocity of this point W, which is moving with the wind. It's a good way to think of it actually. So point W is a point moving with the wind, and we will be interested in the velocity of point P relative to point W. Now when we are told that a plane can do 100 kilometers per hour in still air, we mean that the speed of the plane relative to the air or the wind, that's point W, is 100 kilometers per hour. If the air is still, then VW is 0. And the velocity of the plane relative to point W will just be the same as the velocity of the plane. So what do we mean by vector VP? Well, this is the velocity of the plane relative to the ground, if you like. So when we say we're looking for the velocity of the plane, it means we are looking for the velocity of the plane relative to the ground. We could put a G in here to emphasize that, but normally we don't do that. We can think of this as the absolute velocity of the plane. By absolute we mean the velocity of the plane relative to the fixed ground. But if there's no wind, then the velocity of the wind relative to the ground is 0. So the velocity of the plane relative to the wind is just the same as the velocity of the plane relative to the ground. Now for the outward leg of the journey, intuitively we know that the velocity of the plane will be 100 minus 10, which is 90. Well, 90I I should say. The velocity will be pointing to the right. Okay, because the plane is flying directly into the wind. So we expect the velocity of the plane relative to the ground is going to be 90I. Let's just see this from the formula for relative velocity. So here's our formula for relative velocity. The velocity of point P relative to point W is equal to the velocity of P minus the velocity of W. Now since the plane is moving from point A to point B, we know that VP has no j component. So we could write VP as VP without an arrow times I. Of course we could use anything here for VP. We could just say A times I if we like. But I will just say VP times I, just to remind us that VP is the speed of the plane. The speed is a positive quantity, so we see that we have a vector pointing to the right. That's exactly what we want because the plane is moving to the right from A to B and it's got no j component. And the speed is constant as well. So, you know, that's a bit simplistic, you know, to say that plane speed is constant, but that's what we'll deal with here. Okay, minus VW, well that's minus 10I, that's plus 10I. And we can write this as VP plus 10 times unit vector I. Now, we happen to know the magnitude of this vector, VPW. We know that it's 100. So how do we get the magnitude of a vector? Well, we square the components and add them. Well, the j component is 0. We square the components, sum them, and then take the square root. Well, this is just going to give us VP plus 10. It'll just give us what's in front of I, provided what's in front of I is positive, and it is because VP, the speed of the plane, is positive. Speed is a positive quantity. Okay? So VPW we are given is 100, the speed the plane can do in still air. So the speed of the plane relative to the wind is 100. which means that the speed of the plane relative to the ground is 100 minus 10, which is 90. Now, since vector vp is vp times I, since the plane is moving to the right, we get 90I. Now let's get the time taken for the outward journey. So I will let t stand for the time taken for the plane to go from point A to point B. Since the speed is constant, it's equal to 90, speed is distance travelled divided by time taken. And if we turn that around, we get time taken is distance travelled divided by the speed, which is 90. So the distance is in kilometers, the speed is in kilometers per hour, the km's cancel out. If we multiply above and below by h, our units are in hours. We get 3 1/3 hours. Okay, so the plane flies with constant speed from A to B, and instantaneously it reverses its direction and moves with constant speed from B to A. Now, in reality, that never happens, of course, but we are making that simplifying assumption. So this should be 100. So we are assuming that for the entire journey, the speed of the plane relative to point W is 100. Now, since the plane is moving from point B to point A, we know the direction of vector Vp. It's in the minus I direction. So we could write vector Vp like this, where Vp is the speed of the plane, and of course that's positive. So by sticking a minus sign in front here, we get a negative velocity. We get a velocity in the minus I direction. So Vp is a vector pointing to the left. So as before, Vpw is Vp minus Vw. Of course, that formula always holds. It's just that Vp is different in this situation. Now we're dealing with the return journey. Well, we'll refer to it as the return leg. Outward leg plus return leg constitutes the entire journey. Okay, so intuitively we expect Vp to be minus 110I. Okay, because the plane is moving with the wind. So we just add 10 onto 100. Let's see this from the formula. Vw is minus 10I, so we've minus 10I, that's plus 10I. Okay, we know that the speed of the plane relative to the wind is 100. This is the magnitude of a vector, it's always positive. So to get the magnitude of this vector, we could square the I component and add on 0 squared, then take the square root, or we could just get the magnitude of what's in front of I. Okay, we don't have any I here now. Okay, we no longer have a vector, we just have a magnitude. Now there are two solutions to this thing here. If Vp is 110, then we get the magnitude of minus 110 plus 10. Well, that's the magnitude of minus 100, which is 100. So that checks out. The other solution is minus 90. So we'd have minus 90, that's plus 90, plus 10. So that gives us the magnitude of 100, which is 100. So both of these solutions check out, but which is the correct one for this situation? Well, we want vector Vp to be pointing to the left in the negative I direction. So for that to happen, Vp has to be positive. By the way, Vp is always a positive quantity, so we could disregard that straight away. Vp is the magnitude of a vector, so we can't have a negative solution. Now to get the time taken for the return journey, we take the distance, which is 300, and divide it by the speed of the plane, which is 110. So these units cancel out. We've 300 divided by 100 over h, multiply above and below by h. When we work this out, we get 2 8/11 hours. Now we can answer question 1. We just take 3 1/3 and add it on to 2 8/11. So we add the times for the outward and return journeys. To 3 decimal places we get 6.061 hours. Now for question 2. In question 2, no wind is blowing, so the velocity of the wind is 0, so W is just a stationary point in the still air. So the speed of the plane relative to the ground, or the absolute speed of the plane, is the same as the speed of the plane relative to the wind. Well, the wind is just still air in this situation. Okay, so the plane moves with a speed of 100 kilometers per hour from A to B, and a speed of 100 kilometers per hour from B back to A. So we are assuming that the plane is moving at constant speed from A to B and back again. So it doesn't slow down to reach B, it just stops instantaneously, reverses direction, and moves at speed 100 back to A. So the time to do the outward journey, to go from A to B, is the distance 300 kilometers divided by the speed, which is 100. And that's 3 hours. So as you can see, it takes less time for the plane to go from A to B when there's no wind than it does when there is wind. When there is wind blowing towards the west, it takes 3 1/3 hours. Well, that's not surprising. Now the return time is also 3 hours, and as you can see here, the return time is longer than it would be if the wind is blowing behind the plane, helping the plane along. Okay, 3 hours is greater than 2 8/11 hours. Notice that the total time, 6 hours, is less than the total time when the wind was blowing. Now you could imagine applying this result to the case of somebody swimming in, say, up a river from point A to B. Okay, so we would have a river flowing in this direction. A person flows against the river at a constant speed, and we're assuming the river is flowing with a constant speed, and then the person flows with the river for the return journey, and it will actually take them longer to swim from point A to B and back again than if the water was still. Now in question 3, we are going to consider the situation where the wind is blowing from the south. In this case, we are assuming that the wind has the same speed as before, a speed of 10 kilometers per hour, but it's blowing with a constant velocity of 10 J as the plane flies from A to B and back again. So, as before, the speed of the plane relative to the wind is 100 kilometers per hour. So the plane starts here at point A. Now we want the plane to move east. So we want its velocity, Vp, its velocity relative to the ground, to be entirely in the I direction, no J component. Just like before. So even though there's a wind blowing north, we want the plane to maintain a straight line course from A to B. Now let's get the velocity of the plane relative to the wind using our relative velocity formula. So we get Vpi minus the velocity of the wind. Well, the velocity of the wind is plus 10J. Notice this time that the velocity of the plane relative to W has a J component. So this vector here represents, well, it's the velocity of the plane, but Vpw has a negative J component, so Vpw actually looks like this. So in order for the plane to fly from A to B in a straight line, it has got to kind of veer into the wind. So that it's blown back onto a course, a straight line course from A to B. This is just like the video for the boat on a river, where the boat has to enter the river at a certain angle upstream in order to go directly across the river. Here the plane has to go directly from A to B, so the plane has to fly at a certain angle upstream. Well, in this case the stream is the wind, upwind if you like, so that the plane stays on the straight line course. Notice that the I components of both of these vectors are the same. So if we project the tip of Vpw onto the horizontal, we see that the projection of Vpw is just vector Vp. The vertical component is minus 10J. Now we know the magnitude of vector Vpw. The magnitude is 100. So in order to find out the speed of the plane as it goes from point A to B, we have to get the magnitude of this vector. Okay, I could put vertical lines on either side to indicate the magnitude, but I'll just go straight into the calculation. We can square the I component and square the j component. Squaring minus 10 is the same as squaring plus 10, but this thing has to work out to be 100. So we square both sides of this thing, and we get 10,000 on the right hand side. Subtract 100 to get 9,900. So we can get the speed of the plane. So the speed of the plane is 99.5 kilometers per hour. The plane is moving from A to B with that speed. Now it should be clear that the plane will move from B to A with the same speed. Okay, the wind is blowing from the south, so there's no real change as far as the plane is concerned when it flies from A to B and when it flies from B to A. So if we want to get the time taken for the entire journey, we divide the entire journey, which is 300 plus 300, 600 kilometers, by the speed for the entire journey. So the speed is constant for the entire journey. This works out to 6.03 hours. So notice that the time taken if the wind blows from the south is actually less than the time taken if the wind is blowing from the east. Okay, in both cases the wind speed is 10 kilometers per hour. And that fact is true in general. If you imagine the situation of someone swimming from point A to B, where points A and B are in a river, say that's flowing from the right with constant speed, then it takes longer to swim upstream and back downstream again than it would if the person was swimming across the river, across a river moving with the same speed, say 10 or whatever.